Hello, let's talk a bit about how to evaluate cache performance using cloud storage traces. My name is Eviction, and I'm from IBM Research. For the past few years, we have been active in storage research. Specifically, we have been studying how to design caches in a hybrid cloud environment. As part of this work, we collected and used traces from the public IBM Cloud Object Storage Service running on the IBM Cloud. The insights we gained from these traces have been instrumental in a number of projects. And I'm very happy to say that IBM has anonymized these traces and made them available to the research community at large. In this talk, we introduce the traces and give an example of one insight that we reached while working with them. But first, let's talk a bit about caching. What is a cache? A cache is a fast but relatively small storage location where we can temporarily store data fetched from the real remote storage. For example, while a library can be considered a remote storage, your desk is a cache where books you temporarily checked out are kept. A cache can improve performance if its hit ratio is high. A read request is considered a hit if the data being read is stored in the cache. A read request is a miss if the data being read is not stored in the cache, and we need to go fetch it from the remote storage. Caches are everywhere in the computing world. They exist as instruction caches and data caches on chips, as well as massive cloud-based caches. For example, the type of caches that speed up access to movie streaming. In this talk, we concentrate on caches used to speed up access to remote, either public or private clouds-based storage. One of the biggest differentiators between caches is the admission and eviction policy, which control which data enters and which data is evicted from the cache. There are many different types of policies, with two of the oldest and most well-known being FIFO and the LRU. With FIFO, which stands for first in, first out, data items are kept in a queue. The admission and eviction policy is fairly simple. We admit a new item at the tail of the queue and evict from its head. Upon a data miss, a new item is added to the queue, and the oldest item in the queue is evicted. Upon a hit, no change in the queue takes place. With LRU, which stands for least recently used, items are kept in a list, which is sorted by recency. The most recently accessed items are kept at the top of the list, while the least recently accessed items are at the bottom of the list. On a miss, we add a new item to the tail of the list and evict an item from the list head. On a hit, unlike FIFO, we need to update the list by moving the accessed item to the list tail. So which is better, LRU or FIFO? Well, traditionally there has been a consensus that LRU is better, performance-wise. If we look at studies going back to the 80s and 90s, we see study after study coming forward and claiming that LRU is simply better. For example, here's a study from 1990 saying LRU policy always performs better than FIFO. Here's another one from 1991 saying LRU is almost always superior to FIFO. 1992, LRU is better than FIFO. In 1999, LRU is better than FIFO. We can see a motive here. So, does that still hold true? Now wait a second. Why won't this assumption that LRU is better hold true? Well, there are two good reasons. First, new workloads have emerged in years since those older studies took place. In the old world, where those FIFO versus LRU studies have been published, data was traditionally stored on file or block device. But today, we have object storage, such as S3 and IBM Cloud Object Storage, which have become the de facto go-to cloud storage. Object storage, with its RESTful API, lower cost but potentially higher latency, and eventual consistency, is fundamentally different than both file and block storage. Also, today, we have multimedia, social networks, big data, and machine learning with its massive data sets. All of these things barely existed 30 years ago. Now, talking about big data leads us to the second change in the computing scape, which is the new scale of data. Data today is orders of magnitude larger than data was back in the 90s. As a matter of fact, there are studies that show that of all the data stored on computers today, most of it was created relatively recently. This is because data has a tendency of never being erased, and with practically unlimited cloud storage and data-hungry AI workloads, this trend only accelerates. The remote data can now potentially be located on the other side of the world, either in a different office branch or on cloud storage. And while in the past, caches were generally stored in hardware or in fast memory, cloud storage with its massive storage repositories paved the way for large caches that are so large they can no longer fit in memory and must be stored in larger and cheaper persistent store. The emergence of persistent storage caches gave us caches that are so large that their metadata is larger than the available memory. What we found when we studied such caches is that the old world assumption that the cost of metadata updates in the cache management being negligible is simply no longer true. This in turn results in some interesting findings, but we'll get to that in a few moments. Let's first describe the problem we're trying to solve. In our system, data resides on a remote hub, where the remote hub can be a private or a public cloud. The point is that the remote hub contains lots and lots of storage. In essence, the remote hub is considered to be of infinite scale. In other words, very large. In addition to the hub, we have spokes, where a spoke might be running in a branch office, and this is where the actual work using the data takes place. A spoke contains a local, limited scale cache whose purpose is to improve the access latency to the data. While the cache on a spoke is limited, it can still be fairly large. Hundreds of terabytes, for example. With a cache this big, we may not be able to fit the entire metadata in memory, and we will need to store at least some of it on persistent storage. Here's a diagram comparing the metadata access for FIFO and LRU. In the context of this work, metadata is the data that's used to manage the cache. It contains information on what's in the cache and is used for making insertion and eviction decisions. New metadata is inserted at the tail, while older data is evicted at the head. We keep the head of the FIFO queue and the LRU in memory to minimize the amount of I/O. And we do the same with the tail. So while the body of both FIFO and LRU are on persistent storage, a set of recently inserted items and a set of candidate items for eviction is kept in memory. Upon a data miss, we need to insert a new item and update the metadata both for FIFO and LRU. But upon a data hit, we only need to update the LRU metadata. We do not need to update the metadata for FIFO. This is because LRU cares about recency. So the LRU list order changes upon a hit, while FIFO does not care about recency, and therefore no change in its queues takes place during a hit. This small change in behavior turns out to have significant impact on performance, as we shall soon see. While the older studies assume that the cost of the cache hit is trivial, this is no longer true. With the bulk of the metadata residing on slower persistent storage, there is a measurable cost for updating the metadata. Consequently, when evaluating FIFO and LRU admission and eviction strategies, looking at hit rate alone is not sufficient. We decided to account for the persistent storage latency using the following cost model. Now note that this is only a model. A cache has many different factors that affect it, and here we are looking at the ones that we believe are significant. HR stands for hit rate. Note that the miss rate is 1 minus HR. L stands for latency. The cost for LRU is composed of the cost of handling a hit, which is the latency for reading the data from the cache and updating the metadata, plus the cost of handling a miss, which is the latency of fetching the data from the remote store. The cost for FIFO is composed of the cost of handling a hit, which, unlike LRU, includes only the reading of the data from the cache. There is no update for the metadata, plus the cost of handling a miss, of course, which is identical to that of the LRU. So what do we have at this point? We have identified that the old assumption that LRU is better than FIFO may no longer be true in our modern computing environment. We have designed a cost model that accounts for latencies that have been ignored in the old models. What we need now is data. Lots and lots of data. Lots and lots of data to go and run experiments and evaluate the differences between LRU and FIFO using our cost model. As already mentioned, storage research is often based upon experiments ran against traces taken from real-world systems. But data is the new oil in our world. It's valuable. And just like oil, it's not that easy to find. Luckily, we had access to just that kind of data in the traces of the IBM Cloud Object Storage Service running on the IBM Cloud. Now, I'm going to jump the gun right now and tell you that this data is available for you to go and play with. IBM has been able to make this data available and give it to SNIA, who is hosting it now on SNIA IOTTA repository. You can find it right there on that link. If you go to SNIA IOTTA and search for IBM object storage traces, you're going to find it. And frankly, I'm looking forward to finding out what kind of delightful insights you're going to be making using this data. So I encourage you all to go there and download it and give it a try and see what's there and just run with it. There's lots and lots of interesting data to be found there. Each trace contained the REST operations issued against a single bucket in the IBM Cloud Object Storage. Each trace was selected based on a single criteria that it contains at least some read request. In total, we picked 98 buckets, or you can think of them as 98 workloads, and we generated traces for these 98 buckets. Each trace was generated over a single week in 2019. There are 98 traces. There are 88 gigabytes in size altogether. The traces represent 1.6 billion RESTful requests, and they're accessing 342 million unique objects. Here's an example of what the traces look like. Basically, the traces contain get, put, head, and delete request, where each request includes the timestamp when the request happened, the request type and object ID, the size of the object, and a start and an end offset if needed. You may need additional information, such as the typical latencies, and you can find them in the link that I'm providing here, courtesy of IBM, of course, so you don't need to reverse engineer it. Some observations about the data. In terms of access frequencies, what we see is that the traces are all over the map. Some traces are completely random in terms of their access frequencies. Other traces show very, very well identifiable patterns. For example, an access every few minutes, every few hours, every few days. And it's basically all over the map. We also have some information about the types of objects that are in the traces, how many of them there are in different categories, and the total capacity of each category. And basically what we see is that just like the access frequencies, the object sizes are all over the place. There are objects that are tinier than a kilobyte. There are objects that are larger than a gig. The majority of the capacity of the object store system is consumed by objects that are in the a few megabytes in size, but it's really all over the place. To perform our evaluation, we used 4 different types of traces. Of course, we used the IBM object storage traces, but we also use the MSR, the SysStore, and the TPCC traces available from SNIA IOTTA. We used these traces and tested them against different cache size configurations, as well as simulated different latencies of both the cache and the remote store. And now it's time to evaluate the results of our testing and simulations. We set up to evaluate whether LRU is indeed still better than FIFO. We designed a cost model to help with the evaluation. We generated new data sets that can be used to perform the evaluation. And we ran lots of tests on different configurations. Here's what we found. If you look at pure hit rate, then LRU wins. It's fairly simple. LRU keeps additional information. LRU has recency information which FIFO lacks. So when you're running with a cache that uses LRU, you're going to find that the data that you're trying to read is in the cache more often than if you're running with a cache that's based on FIFO. So are we done? Is that the end of the story? Have we just showed that LRU is better than FIFO? Well, not so quickly. First, notice that yes, LRU wins in terms of pure hit rate, but the cases where FIFO wins, which is the cases here in green, and there is no clear winner, which is here in gray, is almost the same as the cases when the LRU wins, which is red. Yes, it's better to use LRU. It wins more often, but you're going to get approximately the same result, slightly worse if you're using FIFO. However, the picture becomes very different if we start looking at the cost model. So remember, we created a new cost model that takes into consideration the latency of updating the metadata. And when we plug the results of all the tests and simulations into this cost model, what we find is that FIFO wins big time. This is what you're seeing here. FIFO is basically green, LRU is red, the stuff in gray is no clear winner. And what we're seeing is that FIFO wins more often than not. Now, this graph applies for one particular configuration where the latency of the cache compared to the latency of the remote data access is 1 to 50. But we ran these tests with different configurations, and most of the time, FIFO wins. It's only very much edge cases where that does not happen. And FIFO wins fairly big time. If we go and we want to drill down into this, we can take a look at the cost heat map. So I'm not going to go into this in too much depth. If you're interested, then there's a whole paper on this. But what we're showing here is a cost heat map that shows all the different traces that we have used. So each dot is a single trace. There should be well over 100 dots in here. All these dots are coming from the traces from the IBM object storage, the TPCC, the systor, the MSR data sets. And basically what we're showing here is the difference between the hit rate for LRU and FIFO on the x-axis. On the y-axis, we got the hit rate for the LRU. Really what it means is that the further up the graph you go, the higher the hit rate is. The difference between the green and the red is that green and red applies to the cost model. So green means the cost model is in favor of FIFO, red means the cost model is in favor of the LRU. And really what we're seeing here is that the higher up the graph we go, that is the higher the hit rate is, the more the cost model is in favor of FIFO. Simply because the higher the hit rate, the higher the cost of doing the updates of the metadata on a hit. And that is really why FIFO wins. It's those pesky little updates during the metadata updates on a hit. So what have we learned? We learned that it's no longer clear that LRU is better than FIFO. Hit rate does not tell the entire story. And IBM object storage traces provide new insight and opportunities for research. We encourage you to check them out. At this point, I would like to thank my colleagues, Ohad Eitan, a brilliant Technion PhD candidate, which was an intern with us when we did this work, Roy Friedman, who is OHAD supervisor at the Technion, Danny Harnick and Ronen Kat, my colleagues at IBM. And of course, I would like to thank you for listening. Please take a moment to rate this session. Thank you.